Hello everyone, and welcome to today's webinar by LS Instruments. We will be talking about the characterization of nanoparticles in biological and physiological media through dynamic light scattering. This webinar is an interactive event, and I encourage you to submit any questions you may have using the chat that you can see on the lower right side of this webinar window. Before we start, I would like to say a few introductory words for those who don't know us yet. LS Instruments originates from research projects at the University of Fribourg and ETH Zurich. The purpose was to expand the possibilities of standard light scattering and technologies to enable also the characterization of systems in their native state. We specialize in dynamic light scattering, static light scattering, Depolarized DLS, which will be our particle of focus today, 3D light scattering, and diffusing wave spectroscopy. Our guest speaker today is Sandor Balog. Sandor is a senior scientist at the Adolphe Merkle Institute and has extensive experience in light scattering. He currently focuses on the characterization of nanoparticles, mainly for applications in nanomedicine and in vitro nanoparticles dosimetry. So without further ado, I would now like to hand it over to Sandor for the rest of the webinar.
All right, thank you, Colin, for the introduction. So everyone can hear me, then let's start the presentation. So today we're going to talk about characterizing nanoparticles by dynamic light scattering, within that standard, polarized and depolarized dynamic light scattering. So many of you who comes from pharma and medicine, light scattering techniques are one of the most important characterization techniques to study particle dispersions or suspensions. And nanoparticles can be found in therapeutic and diagnostic products, for example, wound management, vaccines, drug delivery, biosensors, and bioanalytics. And using this kind of instrumentation, light scattering is very important for regulatory and research efforts, for example, ensure good quality and good design. So, as you might know, dynamic light scattering is among the most widely used experimental techniques because it's relatively easy to perform. Sample preparation doesn't take much time. At the same time, it's non-invasive and in situ, and one can study both in, let's say, a time and space rewards fashion. So this is the brief content I'm going to go through today with you. So first, some kind of summarizing the basics of dynamic light scattering, then point out what is the difference of depolarized dynamic light scattering compared to dynamic light scattering, and then afterwards, how can we use this technique to characterize particles? For example, how to benefit from depolarized light scattering, which we briefly abbreviate as DDLS, and what to do if DDLS is not available. So the first few slides will be basically a summary. I'm aware that not all of you might be an expert or familiar with the basics, but during the question session, you can ask freely questions, and then I try to answer them as well as I can. Okay, so dynamic light scattering is basically based on a few physical phenomena and some clever mathematics to characterize the size and the dimension of nanoparticles. So basically, the idea is that we have a coherent laser light which scatters from particles. So scattering is basically something that illustrated here. Now imagine that we have, of course, more than one particle in a given dispersion. Actually, the number of particles in standard dispersions and suspension is extremely high, over billions or even millions. So you can imagine that this light that comes in, this laser light, illuminates more than one particle at the same time, as indicated here. And since they scatter light, it means that the light is coherent, and we're going to create, by this, an interference pattern. While the interference doesn't really look exactly like this, but basically this is the same idea. Here what you can see is raindrops on a pond, creating basically a very nice surface wave interference pattern. Now the interference pattern, when it scatters from colloidal dispersion, is rather looking something like this. This is what we call as a speckle pattern because it's composed of speckles actually. And here you can see the variation of dark and bright spots, and of course something in between, and this is resulting from the interference of elastic scattered coherent light scattering from particles. So what we are interested in is so-called single speckles. So here, if you look at closely, you can see identifiable very bright and very dark speckles. Of course, this is a snapshot, And actually, this single speckle pattern is changing in time, constantly varies and fluctuates owing to Brownian motion. So Brownian motion, right, is the thermal motion of nanoparticles owing to the motion of the fluid around it. So it means that due to Brownian motion, the position of these particles basically varies constantly. Therefore, the interference pattern varies constantly, and thus also the speckle intensity varies constantly. So for example, here, number 7, you can see the intensity variation of one single speckle. And actually, this is what we observe through clever optics with dynamic light scattering. We observe the fluctuation of one single speckle, and using and relying on the statistical properties, we can estimate basically how fast these particles are moving, wherefrom we can estimate the size and the dimension of the particles. Most of the time, the quantification, the statistical measure is the so-called intensity autocorrelation function, which is basically nothing else but a time-dependent statistics of speckle fluctuation. Most of you probably who have measured in dynamic light scattering has ever seen this kind of curve. Okay, and by the end, we relate experimentally measured quantity, which is the so-called G2 or intensity autocorrelation function, to the so-called field autocorrelation function G1, where G2 comes because it's intensity, so second order coherence. This is called as first order coherence. This is what we can calculate through theoretical results. We're not going to go through this, but if you have questions later, I can answer some aspects of it. And this is what we can measure, the intensity correlation of speckle fluctuations. So again, just to summarize, so dynamic light scattering is based on these phenomena. We have elastic light scattering, creates interference, which we call a speckle pattern. We select one single speckle, we observe its fluctuations, which fluctuates owing to Brownian motion, and we calculate the statistics. There are two ways or fundamental ways of analyze speckle fluctuation. One of them is so-called photon correlation spectroscopy. This is exactly what you have just seen before. Basically, we compute the correlation function, and using basically a nonlinear parametric fitting, we estimate certain things that could be used to describe our particles. And one can also use actually photon count statistics. Anyway, today we focus on this part, and we continue with this. So this is again a little bit dense figure, but many of you might be familiar. So we just go through. So what we measure with dynamic light scattering is the so-called hydrodynamic radius. So hydrodynamic radius is an effective radius. Basically, this is a hypothetical radius of a sphere, a perfectly round particle that diffuses at the same rate as, let's say, the particle in the measurement. So for example, if you measure ellipsoidal particles, its hydrodynamic radius is indicated here. This is the corresponding radius of a sphere that would diffuse, translationally diffuse the same rate as this ellipsoidal particle. For example, here, this is a polymer chain, which is more or less collapsed. Again, its effective diffusion rate can be described by its hydrodynamic radius. Now, the hydrodynamic radius and the diffusion coefficients, translational diffusion coefficients, is related together by the so-called Stokes-Einstein relationship, where here you can see that basically the diffusion is a strong function of solvent viscosity and the hydrodynamic radius, which is called a capital R. Okay, so this relationship, Ziegler relation, you have seen before, and this is what we use because theory tells us that in case of particles of monodispersion or suspension, the correlation function is simply a negative exponential decay as a function of time, as a function of so-called translational self-diffusion, and there is this Q. This is basically the absolute squared magnitude of the scattering vector, which is basically a scattering angle dependent value. Now, there are instruments where you can vary this Q, and there are instruments that come with fixed Q. Doesn't really matter at the moment, but this is something that basically scales as a sinus theta over 2, where the theta describes the excuse me, the scattering angle. Okay, and then afterwards we have the correlation function, and from that R is usually obtained by means of parameter estimation via nonlinear fitting or regression. With these equations, we can relatively easily account for polydispersed samples because it's very rare that samples are monodispersed. Actually, there is always some polydispersity. Usually, if the polydispersity is less than 10%, we call that fairly monodispersed. Anyway, through the Laplace transformation, we can also develop the theoretical model to describe polydispersed samples. Now, you remember my Colin mentioned at the very beginning, right, that LS instrument is specializing in different instrumentation and different settings regarding dynamic light scattering. And here you can see, for example, that depending on the particle concentration you have, you might need to use different techniques. So when your sample is very turbid optically, so it means the particle concentration is fairly high and the refractive index is fairly different, then what you have to use is diffusion wave spectroscopy. What we refer to today is so-called dynamic light scattering, right? When our sample is very dilute, at least dilute in scattering and optical sense. It means that we can neglect interparticle interactions, interparticle forces, and we can also neglect multiple scattering light. So this is one idealized case, this is another one. Somewhere in between, when the particle is fairly turbid, but at the same time fairly dilute, so there is a range, then one can rely on so-called 3D DLS. But this is not the subject of this study. But what I just want to say that what we're going to talk about, keep in mind, we always think of samples like this, fairly transparent optically. If it has color, it's not a problem itself. When it's a problem when it comes to DLS, that when it becomes turbid, then one has to use so-called 3D or cross-correlation DLS. Okay. So we can distinguish now light scattering in terms of polarization, right? So this is an idealized scenario. Here, this is our incoming laser beam, which is usually linearly polarized. I mean, a standard laser provides you linearly polarized light. So it means the polarization we term as vertical and vertical. Okay. Now here we have a scattering event and a scattered light is getting to the detector. So in front of the detector, we can use polarizer, or we not necessarily need to use polarizer. When there is no polarizer in front of the detector, this is actually what we call standard or classical DLS. When we have a polarizer, no, the polarization state can be in two directions. Can be parallel to the laser's polarization. This is what we call again VV, or can be perpendicular, so 90 degrees off. And this is what we call depolarized dynamic light scattering. So when we have two polarizers and they align the same way, so parallel to the laser polarization, this is what we refer to in strict terms as polarized DLS. When we have the laser polarization, which is cross-polarized basically, then we have depolarized dynamic light scattering. So basically two polarizers, one before the sample and one after the sample. Now you might ask, okay, where is depolarized scattering coming from? It's coming from optical anisotropy. So optical anisotropy means that, for example, here we have this hypothetical particle. Its refractive index not the same in this direction and in this direction. So it means that when a light wave comes in, right, polarization is different in the two directions. In this case, polarization in this direction is larger than polarization in this direction. Accordingly, the polarization of the nanoparticle or particle is anisotropic, and the resulting vector of the outgoing or the scattered field will be turned away from the original incoming field. This is resulting in a scattered field that has a different polarization than the incoming field. So this now copied here. And it means now this depolarized field has two components in the coordinate system of the incoming laser. One is parallel, one is perpendicular. So this is what we call depolarized scattering when we observe this perpendicular phase, and this is what we call polarized dynamic light scattering. When we do not have a polarizer, then we observe the fluctuation of this vector, and this is standard light scattering. All right, so what kind of particles are optically anisotropic? So typical case, gold, silver, rods, long, elongated particles, aggregates actually depolarize light fairly well. Genus particles, depending on what is it made for. And for example, large silica particles. When the particle is fairly large, depolarized component can be detected because actually no material is really homogeneous. It just depends on what is the length scale you look at it. Okay, for example, these are gold nanoparticles, and here one can see clearly the optical anisotropy, at least the origin of it. These are fairly nice gold nanoparticles, but actually, you look at them closer, you can see that they're not perfectly spherical. They're fairly round, but they're not at all spherical, and also there are inhomogeneities within their structure. Here you can see these are fairly potato-like particles, and I didn't show the image here, but you can even see that basically within the crystalline volume is not identical. You have different crystalline domains, and it means that their polarization is different depending on the direction. Nonetheless, if you have particles something like this, they're fairly round, so it means that you can describe them fairly well with a spherical model. So it means that the translational diffusion coefficient remains the same as it was described by the Stokes-Einstein equation. So it means that it's inversely proportional to the hydrodynamic radius. Of course, it might happen, right, that most of the time the particles are somehow functionalized. Let's say there is a polymer shell around it. Of course, in this case, the hydrodynamic radius is not the particle core itself, but something that is defined by the polymer shell. Now, once you have depolarized scattering, you can measure rotational diffusion coefficients, because particles, right, in the fluid, they're not just wiggling randomly and moving randomly owing to Brownian motion, but also the orientation changes randomly, so they rotate back and forth, back and forth. Basically, it's just what is diffusing is their rotation. In this case, if we have round or fairly round particles, the rotational diffusion, you can see the dependence is different. Basically, proportional, inversely proportional to the volume of the particle, right? Because 1/3 is basically proportional to the volume of the particles. So you can right away see the similarity between translational and rotational diffusion, right? They both inversely proportional to the viscosity, but the big difference, there is a 1/r dependence here, and there is a 1/r² dependence, third cubic dependence. Therefore, the dependence of rotational diffusion is much stronger than the dependence on translational diffusion. Okay. Now, polarization matters because if you are not aware of the fact that your particle actually do scatter depolarized light and you do detect it, then it means that, for example, it can happen that you measure a bimodal correlation function. For example, here you can see these gold particles actually measured at different angles, 15, 30, 60, 90. So if you happen to measure and you realize there is a bimodal correlation function and you're not aware of the fact that this is coming from depolarization, you might assume that, actually, my particle system is bimodal. You look at PM, but you don't see any bimodality. So what is the problem? So there is no problem at all. Simply, it comes as a fact owing to depolarization. So as soon as you have depolarized component and you measure polarized or standard dynamic light scattering, you will have two components. One part that would corresponding to standard dynamic light scattering, translational self-diffusion, and there will be another part which is described here, that would correspond to depolarized scattering. So if you will measure only depolarized scattering, and this will be a corresponding correlation function at different angles, then in case this is, you can see that you have two components there. There is a rotational diffusion, and there is a translational diffusion, right? So when you measure standard dynamic light scattering, these parts, they are here. So it means that here they're going to show up. So the first decay actually corresponds to depolarized light scattering, and the second big decay corresponds to standard light scattering, that is translational diffusion. Okay, so when to watch out? When you can expect to see a bimodal correlation function that has nothing to do with the size distribution or the modality of your particle dispersion or suspension. So typically particles that promote depolarized scattering, optical anisotropy, you have shape and/or internal inhomogeneity. For example, your particles are somewhat crystalline or highly porous. Typical cases, metallic particles, gold, silver. Long elongated particles like rods, fibers. Again, crystalline or semi-crystalline particles, aggregates, agglomerates, particle clusters, for example, dumbbell particles, genus particles. Again, large particles, and also it's frequent powder particles, for example, zinc oxide, titanium dioxide that are derived from powder and disperse. They also depolarize light fairly strongly, and it is possible to measure them. And if you do not watch out, then you might misinterpret the correlation function. Okay, so how does it look like from instrumentation point of view? So this is an instrument we use at our institute. This is the LS spectrometer. This is a goniometer-based instrument, which means that the detection angle we can vary in a fairly wide range. So in our case, the minimum angle we can access is 15 degrees. The maximum angle we can access is 150 degrees. So we can basically change the angle of detection. So the first polarizer is here. This is just the point where the laser is exiting. Basically, the optical setup, laser goes through, focused onto the sample, wherefrom scatters into the detector. So the detector is here, we don't see it, the front, but it somehow looks like this from point of view, where we have basically the second polarizer, which we call now analyzer, and it can be in two states. It can be in VV, so it means the polarization is identical to the polarization of the laser, or can be in so-called VH direction when the polarization is perpendicular to the incident one. So this is what we use when we measure dynamic light scattering. This is what we use when we measure depolarized dynamic light scattering. Okay, so for example, how can we do this? I show you two examples. These are here cellulose nanocrystals. So actually, they really look like very, very long and thin rod nanoparticles. Mathematical model describing this kind of particles works very well. There is another case, for example, gold nanoparticles. These are fairly nice and well distributed, relatively short gold nanorods. And using depolarized dynamic light scattering, we can actually measure and characterize the dimensions. So I show you one example in case of cellulose nanocrystals. So here we have basically 2 degrees of freedom to describe the particle geometry. So one could say that the dimensionality is equal to 2. We need to know the length and we need to know the width. So there is a fairly simple mathematical model. I'm not going through the details, but basically what you can see, that both the translational diffusion and the rotational diffusion is a function of length and width. Actually, L over WV, so length over width, this is what we call aspect ratio. So it means that we have a mathematical model which we can use to interpret experimental data, because we know that the depolarized correlation function is of this form, and if we measure the relaxation rate, which is recorded as gamma, at different angles, this is low angle and this is high angle, we got something that will define a straight line, and simply by fitting a straight line to this, we can determine the translational diffusion and the rotational diffusion, right? So we have 2 parameters we obtained. So we have 2 unknown parameters. So if the measurement is made well, basically from this, we can calculate both the length, both the width. For example, if you want to do this for this gold nanorods, the process is very similar. What changed is the model. But these models existing were very, very fairly accurate and very good calculations. One can use this to calculate. Okay, so now I finished basically the introduction to dynamic light scattering and depolarized DLS. The next section will focus on particle characterization. So many of you, I'm sure, are aware of the fact that biological and physiological media actually are fairly complex and fairly crowded fluids. So this is a number to scale figure where basically a nanoparticle is illustrated in cell culture medium. So this is a standard cell culture medium used in biological laboratories or live cell laboratories, etc., etc. And here you can see that actually a cell culture medium is very crowded. You have proteins, you have ions, amino acid, and vitamins. So here these purple balls actually indicate proteins. So you can clearly see that, yes, actually around the particles there are a huge amount of proteins. So this is at 100 nanometer length scale. Then you go down and you see this is the protein and this is the protein. And here, let's say a detailed list of the components. What actually matters is the number of proteins, because ions are fairly small, amino acids are also, and vitamins are fairly small compared to, let's say, typical proteins found, for example, in serum or plasma. Okay, so the possible consequences of this, depending on the particle type and the particle stability, you might have proteins absorbing onto the surface, your particles might aggregate, your particles may dissolve, or simply if your particle is surface functionalized, so let's say you have some kind of polymer attached to the surface that, let's say, the goal would be enhance colloidal stability by steric repulsion. It can also happen that simply there is a ligand exchange. So the good thing, however, the dynamic light scattering is very sensitive to these changes. So by using dynamic light scattering, you can basically find out what's happening with your particle, whether there is a protein corona, meaning proteins absorb onto the surface of the particle, whether you have aggregation, dissolution, or ligand exchange. So this is why light scattering is fairly used. Okay, but the challenge at the same time, those proteins. So you can see there are fairly a lot of proteins, and it means that proteins, you can think of them as basically biological nanoparticles, right? Because the proteins are not too small. Let's say typical proteins range between, I don't know, 2 to 10 nanometers in radius approximately. So it means that they do scatter light. So you have now a system which is complex because you have nanoparticles and you have proteins, and they both scatter light. So the light that reaches the detector contains light scattered from the particles, light scattered from the proteins. So maybe you remember right from the very beginning, in order to quantify and determine or characterize the particle size, we calculate and use the statistics of these light scattering reaching the detector. But now it means that we have light scattered from the particles and the proteins. Accordingly, the statistics, like the correlation function, will also contain contributions from the particles and the proteins. So for example, plasma or serum may include proteins up to 8 microgram per milliliter, plus electrolyte, antibodies, antigens, hormone, etc., etc., etc. So this might be very problematic in analyzing dynamic light scattering of nanoparticles in physiological media or biological physiological media. So what is the consequence? So when a particle system is dispersed in a medium that is full of proteins, a correlation function will be composed of at least 2 terms. One corresponds to the particle system, and the other one corresponds to the medium. So these are just simply factors. Basically, it's a normalization factor because we know that a good quality correlation function is basically the amplitude of it. It's 1, but it means that when it's time 0, this goes to 1. So these basically just normalization constant. But now, depending on your particle concentration and the medium type you measure, this can be very small and this can be very large. I mean, if you're lucky or your system enables it, this is very large and this is very small compared to this. But this is rare. Most of the time, this is fairly large and this is, if not larger than this. Anyway, this is present. So for example, this is actual experiment where CCM indicates cell culture, medium, these are nanoparticles, the red line, and the green indicates nanoparticles in cell culture media. So those are actually standard particles, I think silica particles. The size, if I remember right, I think something like 75 nanometers. I'm not sure, but doesn't really matter. But those are standard scenarios where you can see that the cell culture media, the overall scattering intensity, is nearly as high as the scattering intensity from the particles. So it means that when you look at the correlation function of the particles in cell culture media, which here is again the green curve, you must find 2 components in it. One coming from the cell culture media and one coming from the nanoparticle, depending on what happened to the nanoparticle. Maybe you remember here, right? These are the basic scenarios that can happen. Whether there is a protein corona, there is aggregation, there might be dissolution, ligand exchange, etc., etc. So it means you have 3 unknowns here, right? But you know that the cell culture media is somewhere here in this green function, and also there somewhere in the nanoparticle correlation function, which is different than the nanoparticle correlation function in water. So it means this is not trivial to analyze. So for example, if you just analyze this green curve without thinking of this problem, the presence of protein, what you will get, you most likely will get the results. Actually, your nanoparticles become smaller and they become very, very polydispersed. This would be because simply the 2 components, one component, second component, increases polydispersity, and given the fact that most of the time the proteins are smaller than your particles will decrease the apparent size. And this, for example, if you try to do with contin and other kind of, let's say, algorithm that actually very efficient in many scenarios, will be very difficult to separate nanoparticles and proteins. So the first thing, and here where one can really benefit from depolarized dynamic light scattering, because many particle types that, let's say, interesting in pharma or other kind of applications promote depolarized scattering. So this is, for example, silver particles. Silver is interesting for pharma, the way I know it from many points of view, for example, addressing wound management problems, but silver also scatters depolarized light very well. So how can we do this? Now the trick is here that since silver is scattering depolarized light very well, it means that there is a very good contrast in favor of depolarized scattering. So this is now here illustrates the polarizer in front of the detector. So now here the polarization indicated by this red arrow is so-called VV, that is vertical, that is we study standard or polarized dynamic light scattering. Now it means since we have a lot of proteins around, we do see them in the detector, right? The polarizer itself is not filtering out the scattered light from the proteins. So it means we will have this correlation function that contains one term from the particles, one from the proteins. But if we turn the polarizer 90 degrees, right? Now this is the polarizer, so this is now vertical, horizontal. Then it means compared to the particles, the depolarized scattering from proteins is so weak that you basically do not see them. So what you see is only the particles. This is a passive filtering, but extremely effective, because here you can have a correlation function that is free of the contribution of the proteins around the particles. So you can really access, let's say, information describing whether those particles are aggregating or dissolving, or simply just there is a protein corona, or there might be something else going on. Okay, so how do we do this? Again, we go back, right? This is basically the layout of the instrument. This is, oh, this should be a WV here. So not WV, but 2 times V. So VV. I forgot to put it there. I'm sorry for that. But anyway, what matters here, right? That here is this polarizer in front of the detector. We just flip it, turn it 90 degrees, and right away we filter out the contributions from laser. Okay, so let me illustrate the selectivity with actual data. So this is silver nanoparticles, the same silver nanoparticles you have seen before in water, and afterwards in RPMI plus supplemented FBS. This is fetal bovine serum. Usually the supplement is 10% NES, the way I remember correctly. Anyway, and then what we can see here. So this is standard scattering. It means we measure VV, polarizer aligned parallel to the laser. It means that we expect to see scattering from the proteins. And indeed, you can see the scattering from the proteins, which is indicated by this green line, is nearly as strong as scattering from the particles. Okay? So it means that the scattering here has contribution from this part, and the same will be in the correlation function. Now, when we measure depolarized scattering, you can see that basically the silver particle, the scattering from silver particle is much, much bigger than scattering from the proteins or the cell culture media alone, right? I mean, this is 1, this is, let's say, 0.01. So anyway, even the worst case scenario, we have at least a 10-fold improvement, if not more. Okay, so this is great. This is good. This is what we want. So we can really filter out scattering from the polymers, proteins. Okay, so this is great when you have this kind of particles. Now the thing that, alas, not every kind of particle system promotes optical anisotropy. So for example, spions, they can be synthesized in a fairly broad size scale. They're fairly nice, very nice nanoparticles, but somehow depolarized scattering is very weak from them. There are also other kind of particles, let's say liposomes that are not too large, most polymeric particles, etc., etc. Actually, many particle systems that are interesting as drug delivery system, they do not really come with useful optical anisotropy, unless they are very special in certain regards. So what to do when DDLS is not an option? So what to do when you have this two-component correlation function? Then what you have to do, you have to measure your cell culture media before the experiment. You analyze or approximate its correlation function, and you have to remember it, because afterwards, when you interpret the full correlation function from the particles, in this case in plasma, then you will have to remember and use that contribution to estimate what is the particle size or what is the particle dimension and characteristic. This is a very good approach if you assume that the correlation function of the protein-rich media is not changing just because you add the particles. So basically, you can say that there are many, many more proteins than particles you add. And this is actually a fairly safe assumption, because most of the time, the protein is way more, much, much higher number than the number of particles. This is simply a question of concentration. So it means that if this is the case, then the correlation function of the media does not change. So you can use it to fit the full correlation function. So here, for example, this is an example. These are nanoparticles in blood plasma. And you can see this is the contribution from blood plasma. This is the contribution from the nanoparticles. And this is the full fit or the full interpretation. And you can see the fit is very good. If you look at the residuals, basically this is the residual between the fit and the actual data. We can see that the residual is fairly smooth, fairly flat. So we can accept this as a good interpretation of the data. And from this correlation function, we can calculate now, let's say, all the quantities we are interested in. We can estimate a size distribution, we can estimate an average size, etc., etc. Okay, so as a summary, so biological and physiological media do scatter light, which is a challenge for nanoparticle characterization with standard dynamic light scattering. If you have the option of DDLS, so you have an instrument, for example, which basically just takes a good filter or two, and you have the chance to work with particles that promote optical anisotropy and depolarized scattering, then your case is much easier. If not, then you have to do a little bit of, let's say, either seek for help from an expert, or you have to be ready to do some more analysis and a little bit of math interpreting the data. But the fundamentals are fairly simple. You have to keep in mind you have two contributions. You have to know one in order to estimate the other. All right, I think we are finished this part. Here, I think you will have access to the slides. So here I listed some of the publications we published, I don't know, in the last 5-6 years that relates to dynamic light scattering and depolarized light scattering and how one can use it. So I'm happy to take questions now if you have questions for me.
Thank you everyone again for joining us today, and thank you, Sandor, for the very interesting presentation and discussions. So let's start now with the Q&A session.